Hi, good afternoon. It is such a pleasure and an honor to be here today with you to discuss some of the items that are currently facing the United States and specifically California Domestic Water Company in its operations with respect to PFAS, which has already been mentioned is an emerging contaminant within the U.S. and is currently going to be regulated by the United States government, the United States Environmental Protection Agency. So this is something we've had to pick up, kind of learn on the fly and really quickly as to the health effects, but it is a significant topic of concern in the United States. So what is PFAS? PFAS are per and polyfluorinated substances, and they're manufactured items. So if you look at some of the everyday consumables and how things are ingested within the human body, you can see that we pick them up from things like food packaging. So if you're going to a fast food restaurant and you're getting something, the wrappers or the actual products themselves may have PFAS on them. Non-stick cookware, so if you're at home and items that have Teflon on them will have PFAS in it, get into your food, and then you'll also be consuming it at that point. Your furniture can have non-stick coating on it and stain-resistant coatings. And so on those, you will also see that if you're sitting with them, you can touch them with your body, get into your bloodstream and things like that. Waterproof products, so clothing that has been waterproof for rain and being outdoors can also have these materials and these compounds on them. And then firefighting foams. Firefighting foams is the main focus for water systems, primarily in the US, specifically for Cal Domestic Water because of where it's located. As firefighters are putting it out, it can leach into the groundwater basins, which is primarily where California Domestic Water Company pumps 100% of its water supply is the groundwater basin. So currently, the groundwater basin is contaminated, and we have to look at and identify best available technologies for treatment, and then how we go about treating them to remove them from the drinking water to ensure that the public that's going to consume the drinking water will not be ingesting those compounds. These contaminants are currently unregulated both at the federal level in the United States and as well as by the state of California. They do have certain standards, but they are not currently regulated. Yet, if you're not meeting the minimum standard that was set by California back in 2018, I believe it was, if you're not meeting certain things, certain standards, certain numbers, certain levels of these PFAS in your drinking water, there are certain actions that you would have to take, which has limited available water supply to the agencies which are serving a specific service area. So if your water source well exceeds that minimum level, you're required to take it out of service. Or treat it and figure out what you're going to do to ensure that you're going to meet that minimum standard. And that even comes with it not being a regulated contaminant at this point. But what the US EPA is currently looking at setting two primary threads, PFOA and PFAS, at 4 parts per trillion. Parts per trillion, I mean, we're getting into technologies now that are detecting at that low level and even lower than that. They will look to eventually try and set these contaminants even lower than 4 parts per trillion. California has a history of being extremely stringent in how it sets its contaminant levels, what we call maximum contaminant levels. And so we would assume, based on history, that California's regulations will set, if the federal regulations are set at 4 parts per trillion, California will look to probably set them at least 2 parts per trillion. That's based on history. We're usually typically about half, if not lower, which is going to impact and affect thousands of water systems throughout the state of California and really across the United States, because this is a global problem. It's everywhere, as we discuss here, and you'll see. So why, in California and across the US, we've kind of given them the short name of forever chemicals. And why is that? They persist within the environment. They are not easily destroyed. They can accumulate in soils, groundwater, surface water, and in the atmosphere until they are actively removed and destroyed. So these things persist, they are around, and they will be around forever. So the solution, or one of the items that I'm going to talk about today, is what do we do with some of the waste streams from some of these items to ensure that we're not re-emitting them back into the environment from which they're being removed. So this is just a diagram, and I thought it was very interesting. The U.S. Government Accountability Office, they provided a report, and this just shows how in drinking water that's being provided to consumers on how PFAS can get into the water and be introduced. So you can see that farmers would use some of the sludge that can be produced from wastewater systems, and they use that as fertilizer for their land and their crops. But that, if it has PFAS in it from the water that's been put to the waste system, and they've removed it, it remains in the sludge, which is the waste stream from the wastewater system itself, and it can be used in farming. So then any of the crops that are grown, any of the livestock that might be eating whatever crops are grown, that can then be contaminated, and then if the humans are consuming any of the products from those livestock, from the crops, they can ingest that and it gets into the bloodstream. It can have some severe adverse health effects, and that's what we're currently really trying to understand, and that's what the US EPA is looking at in order to determine how they're going to set and how low they're going to set that contaminant level. This slide is primarily to show that this is all around us. It's been around, it will continue to be around until we determine how we're going to test. And testing is becoming ever more stringent because you can start testing to even lower levels than you have been previously. My focus will be, again, on how it gets in the drinking water and then how we remove it from the drinking water and what we do with it after. So for California Domestic Water Company, we're a wholesale water agency. We are the largest mutual water company in the state of California. We operate 7 active groundwater wells that produce up to 25,000 gallons per minute. Specifically for us, we do have a few wells in the same watershed that currently have PFAS detection in them. And the PFAS detection limits range. They start on the very low end where they're below the minimum levels for California, and I have a couple of wells that are extremely high, up to about 40 parts per trillion for PFOA and PFAS. And so what do we do with it? Currently, we have source water production out of the groundwater basin, so we are 100% groundwater producer. And we operate what's known out of the main San Gabriel Basin. So when we pump the water, we then put the water, at least a stream of it, not the entire 25,000 gallons per minute, but through best available technology for us was single pass ion exchange, which is a resin. And so you can see the facility there, their vessels, that's a 3,000 gallon per minute to treat the source water from the well that's currently in the upper right-hand corner. So it treats up to 3,000 gallons a minute and removes 100% of the PFAS that's in there, so I'm treating down to levels that are considered non-detect. We would also consider that zero. We don't typically have hits that are between zero and the detection limit for the testing, which is 4 parts per trillion. So we would consider that zero, it's 100% removed. And then we convey that through transmission pipelines to 3 primary shareholders. Our systems expands about approximately 25 miles of 48-inch pipelines. And again, we have turnouts on some of those pipelines to each of our shareholders. The 3 primary shareholders are 1 investor-owned utility and 2 municipalities that range from the Los Angeles area in Southern California to the Orange County area in Southern California. And so then from that point, it's then delivered to the wholesale shareholders who then use it as a supply within their system and then deliver it to what you would consider the end users or the businesses or the residents. So we're just a supply for that, but overall we do serve about 225,000 businesses, residents, and other consumers. So California Domestic Water Company has a single-pass ion exchange treatment facility for PFAS. So this is a larger picture of it, so you can see it. 6 media vessels that operate in what we call a lead-lag configuration. Lead-lag configuration just means that the water is, each of those 6 vessels work in pairs, which means 2 are working together. Runs through the initial vessel, removes the PFAS utilizing the resin and the ion exchange between the PFAS compound and the innocuous ions that are included on the resin. And then it runs through the second vessel because the regulatory agencies in California are very adamant about ensuring that we have redundancy within our system to ensure that no contaminants that we are currently treating for get through. So typically what you would do is once you operate that lead vessel and it starts hitting in certain areas on the vessel when you're completing your sample, when there are detections of PFAS at specific levels within that vessel, we would have to take it out of service and switch, and we would move over to the lag side and start operating that lag vessel as our lead vessel, and then the lead vessel would then become what we call the polish, and that resin would then be changed out to ensure that we're not allowing any of the PFAS compounds to break through and get into the water system, because we are utilizing the water from this facility to blend with other source waters that we have to minimize the levels of PFAS that are in that water. So the combined blend then meets the regulatory standards that we're required to meet. Again, it operates 3,000 gallons per minute. This facility runs 24/7, so we're producing about 4,800 acre feet per year. 4,800 acre feet, so every acre foot is about 326,000 gallons. So you can see this is a pretty significant treatment facility for what we're currently doing. So the source groundwater for us from this facility is treated to non-detect. It's blended with finished water with our other wells, and then it's delivered to our shareholders. Overall, this facility, I said it's a pretty significant one. But in the grand scheme of things, it's not even, there are other agencies that have much larger scale facilities than this. I only needed one treatment facility to ensure that I could meet the regulatory standards. But this facility still cost about $4.5 million in US dollars for equipment, materials, construction, and regulatory permits and compliance. Annual operations and maintenance costs for this, for California Domestic Water Company, which would include power, labor, water quality testing, regulatory compliance reporting, materials, supplies, and new resin when it's required to be changed, about $456,000 per year, and that's on an annualized basis. So when you look at that and you take both the capital infrastructure and the annual operations and maintenance expenses, which will go up over time. This is based on today's United States dollars. But with inflation and other impacts that would force upward pressure on some of these items, the financial impact is currently $142 per acre foot, which is significant for an operation like mine. However, as I mentioned, we're one of the largest mutual water company in California. There are several smaller agencies where a financial impact like this is devastating to the end user. And so looking for how do we have additional technologies that could be considered best available technologies for smaller agencies that can input a smaller footprint but yet still treat to meet those regulatory standards is something that's needed within the industry. So what does it look like inside? As I mentioned, ion exchange, it utilizes a resin material that's obviously treated to NSF standards to ensure that nothing's coming out with it. So this is an NSF approved resin that we use, and the resin is included in those vessels that you can see there. It removes the PFAS ions from the water, and it exchanges them with the innocuous ions from the resin beads. For PFAS, when the resin capacity is exhausted, it is replaced with new resin. There is no current technology or current best available technology for ion exchange that is regenerable. So there's nothing that we can do at this point. There is for some other contaminants, but not currently for PFAS in utilizing this resin. And even with some of the regenerable resins that are utilized for other contaminants, sometimes those aren't reliable. I've seen one operated at a different system, and some of the waste streams from that are significant. And the sanitation districts who deals with some of the waste streams from that, which would primarily be brine, because the salt would remove on the regenerable systems, and the cost for that can be so extensive that it's not even cost effective to operate systems like that. But currently for PFAS and the resins specific to PFAS, there is no regenerable resin that can be utilized currently. So it's a single pass, you use it one time, and then you're done. For California Domestic Water Company, we anticipate that we will be replacing at least one vessel per year, and that comes at a cost of about $200,000. So I mentioned overall annual operations and maintenance costs look to be $456,000. About half of that is replacing the resin in just one of these vessels. The concern for California Domestic Water Company and several water purveyors throughout California, and it will become an entire issue for the country, the United States, and really on a global scale, depending on what technologies are used to remove these chemicals and these compounds, is how do we dispose? What do we do with that PFAS-laden resin? What are we going to do with it? And how do we ensure that we're mitigating any future risk or liability that the water agency will have for removing the contaminant and the compound from the water to make it safe for drinking? There's two options currently at this point specifically to ion exchange resin. I can either take that resin and send it to a landfill that will accept it. They will do a characterization of the resin itself. It will have PFAS on it. But if I put it in the landfill, then there is the potential over time. The risk for us is that because PFAS is so persistent in the environment, that eventually the PFAS compounds will leach from the landfill into any other groundwater basin that might be around. It could also get into various soil areas, farming areas. I'm not saying that any of that is close to where the landfills are, but there are the opportunity for it to get out and re-emit back into the environment. So we've removed it from one place, the drinking water, where it came from, and I've put it in a different place, and now it's there, and is it going to become a problem in the future? Because if it does become a problem in the future, that liability is with California Domestic Water Company. It's not with any other agency. I'm responsible for it and would then be required to eventually look back and ensure that I can treat that area where it re-emitted to with whatever issues they're going to face from the potential leaching in the future. Same thing with incineration. Because PFAS compounds can persist even under high heat conditions, there's still going to be ash, which is the waste stream from the incineration of the resin. And within that ash, when they've done testing on it, PFAS compounds are still there. They are not removed. They are not destroyed. And so with that, again, after you incinerate it and you have ash, they put it in the ground. It's landfilled. And so once it's landfilled, it's there, and there's still the risk that it will re-emit back into the environment over time with discharges, releases, and other residual PFAS streams that will end up there. So what do we need? There's a couple of things that we're really looking to do and to really understand. As I mentioned, PFAS is quickly evolving in the US. It's not something, they set a specific risk level. They've also set a notification level. And then because of those items and what we've looked at, some of these systems, including mine, have had to understand, well, what's going to be the best available technology for me, And am I going to be able to afford it? How do I incorporate that into my cost structure and into my rate to ensure that I'm recovering everything? So $4.5 million, not all agencies can put that in, even for a smaller scale system like what I have for a specific wellhead treatment. So what do we need? We need more cost-effective treatment technologies for removing and eliminating PFAS from drinking water. It's going to be significant because this will be an issue, especially once the US EPA sets its levels, which is scheduled to be sometime here in March of 2024. And if they accept the standard of 4 parts per trillion, that's going to have a significant impact on thousands of water agencies throughout the United States. Also, are there smaller scale technologies and options for small water systems to limit the financial impacts? Currently, as I mentioned, with California Domestic Water Company, we're a large scale mutual water company, which is not common in California. Most of the mutual water companies are extremely small. They have about between 1,000 to maybe up to 3,000 service connections. And a facility like what I built for $4.5 million can be devastating to that agency, and then they're looking for other solutions or other ways to ensure that they can still provide a reliable and sustainable supply to their shareholders. And so it's not something that's currently been seen at this point. What is considered best available technologies are large-scale projects, and some of the smaller systems aren't able to afford those or to construct them and implement them into their waterworks. And then finally, we need to look at additional research and study efforts to understand the disposal techniques for effectively treating and disposing of PFAS residuals and waste streams to eliminate the risk of re-emitting PFAS to the surrounding environment and its natural resources. Because if we don't do that, we're just setting ourselves up for failure in the future. It's just going to be another item that we're going to have to address in the future in possibly a different area than where you're currently providing service. Because the landfills that we utilize currently are not anywhere close to us. They're in different states. So am I just taking a problem from my current situation with it being in the drinking water, removing it, and then when I'm landfilling it and putting it in a different state somewhere, am I going to have a problem there in the future? So how do we consider that and eliminate the risk for that? Because that's going to be significant as more systems put in these treatment technologies, begin to treat and remove the compounds from the drinking water. They've got to identify how they're going to address the waste from that, and that's significant for us. Thank you. I can answer any questions.